Should we wait a bit or?
You can start.
I will start slowly. So last time I thought I would be able to give you the morphisms for projective varieties, which are defined without any high-tech, like Italian style. Italians were doing algebraic geometry before it became science. It was sort of form of an art for Italian school of algebraic geometry. As a result, most of what they did was wrong. So like about every paper of Italian school of algebraic geometry contained errors. And by the end of the period, there was essentially nobody who could do it anymore because there are too many errors. But it was very classical and you could do everything low-tech. Now, of course, you never do it. You do sheaves. And this is what we shall do, unfortunately. So I would try to do it as little as possible because you need to have examples, and to have examples to work with sheaf later. But today we shall do slightly high tech. So there was already a notion of sheaf of functions. It was, let me remind you, you have a for each set U, so M is topological space. For each set U, you have the sheaf provides you a space f of U, which sits in functions on U. And then if you have, so it is a subset of functions, vector subspace. And then if you have U is union of Ui, you have Fi belongs to the set of sections. This is called set of sections of U, of F over Ui. And then F, you have restriction maps. F of U restricted to F of V for each U, V inside U, this restriction. So if you have a function which belongs to this sheaf of functions, say smooth functions, continuous functions, its restriction is again a section of the same sheaf, so it remains. And you have Fi, this collection of sections. Fi restricted to Ui intersected with Uj is equal to Fi restricted to Uj, well, Fj restricted to Uj intersected with Ui. Then there exists F inside the set space of sections of F over U, such that F restricted to Ui is Fi. In other words, you can glue sections from open sets. Now I am doing abstract sheaves. Abstract sheaves are similar, except that it's not necessarily a sheaf of functions. It's just anything. So for each data of sheaf, in fact, I will give you first data of pre-sheaf. So pre-sheaf and sheaf, they have the same data, but the axioms are different. So what is sheaf, or what data define the sheaf? For each, you have M topological space. Now, the sheaf can be sheaf of anything, like sheaf of sets, sheaf of rings, sheaf of groups. Today it will be vector spaces or rings, but you should be aware that there are even things like sheaf of categories. Anyway, you have M topological space for each open set U inside M, open. There exists a vector space, so we're given this part of data, given vector space F of U, like there, but it is abstract vector space now. It's not a subspace of functions or anything. And we're given vector space F of U, and Yeah, you have restriction maps for each u inside V, given restriction map. Let's call it restriction F. You restrict from V to U, from bigger to smaller. This is, well, this is the symbol of restriction, F of U. So pre-Schiff axioms is the following. There's just one. You have F. Suppose you have a chain of subvarieties V inside of U, inside of W, for instance. Then you have restriction from F of W. You can restrict to U, mapping it to F of U, and then you can restrict it to V, mapping it to F of V. On the other hand, you have a restriction map to V. Should be commutative. This is the only axiom of pre-Schiff. So let me give, for example, as a pre-Schiff. Well, I think we had something maybe in the handouts, but for instance, you can, for each U, you can just have a fixed vector space. Like U goes to just, or V goes to just a single vector space Cn. And all the restriction maps are identity. Good thing. This would definitely work. Okay. But it's not a Schiff. So for Schiff, you need two axioms. First, well, one of these axioms is here. It's a gluing axiom. But before gluing axiom, so the second is gluing, which is here. If you have a section of a Schiff, a collection, you have a covering of a space U by open sets. You have a collection of sections of your Schiff over these open sets. The restrictions are compatible. Then it is obtained by restriction from some section of the Schiff over U, over the union. Okay. And the first axiom is the following. Suppose you have F inside is a section, and then F restricted to UI. U is a union of UI. Again, open cover. F restricted to UI is equal 0. And then F is equal 0. You can think of that as of exactness of the following sequence. You have F of U, then you restrict it to the product of F UI. This should be embedding. Now the second axiom is written as follows. You put here to the product of UI intersected with UJ. You have two maps. The first is restricted to the second argument, so you have Fi inside, so the first arrow. F of UI is restricted to Uj intersected with UI. You consider this as an element in F UI intersected with Uj. In the second map, reverses the order. the same f of ui, but you restrict it now to ui intersected with uj, and you consider it not as an element of fi intersected with g, but the opposite order in f of uj intersected with ui. Okay. So the difference of these two arrows coincides with the image of that. So this is an exact sequence. So this plus, this minus, this gives you an exact sequence, and this is your sheaf axioms. This is similar to what we have. Do you have any questions, comments? So this is an abstract version of the sheaf of functions which we had already discussed a lot, because they were used to define manifolds. Now I'll use, in fact, I will use just sheaf of functions, except for the last slide, and not the sheaves for the definition of algebraic variety. But then, if you want to define projective morphisms, you still have to use abstract sheaves. Questions, comments? Okay. Definition. A sheaf of rings is a sheaf which takes u and maps it to f of u with all f of u being rings, having structure of ring, equipped with ring structure, and this is fiction map, ring homomorphism. Okay, this is so should be sort of clear. You have an example. All the sheaf of functions we considered, like sheaf of smooth functions, continuous functions, like are in fact completely like C infinity functions, Ci functions, just differentiable functions, are in fact rings. You can multiply differentiable functions, and restriction of differentiable is differentiable and commutes with the multiplication. So this is good. You have lots of examples. But in practice, and maybe we shall see that, you really need abstract sheaves of sheaves of rings, and not the rings of functions. No morphisms of sheaves. I don't think we had it. So you have how they denote B and B prime, sheaves. Morphism from B to B prime is a homomorphism from B of U to B prime given for each U open. and satisfying the following, commuting with the restrictions. So this means that you have a commutative diagram such that you have B for each V inside U, B of U. You can map it by our safe. This has, no, let's call it phi. Using phi, you can map it to B prime of U. Then you can map it to B of V. Then this you can map to B prime of V. This is your restriction. This is your map phi. This is the restriction map. This should be commutative. Okay, isomorphism is just invertible homomorphism. The important thing about sheaves is that, okay, if you have pre-sheaf, the kernel and co-kernel of these maps are again pre-sheaves. Nothing to check, because just taking co-kernel commutes with restrictions or kernel. Because kernel and co-kernels are functorial, if you have composition of two maps, the kernel of composition is kernel of first put to second. Anyway, but for sheaves, this is no longer true. You have to work so it's not hard to find two sheaves for which the co-kernel, for kernels it's okay, for co-kernel it can be no longer sheaf. It will remain a pre-sheaf, but it will be no longer sheaf, so you have to work a bit. And this is part of cohomological algebra, which I hope I will avoid giving, unless you want. But it's important. We're not going to use it. What I'm going to use is that you can use sheaves to define algebraic varieties. It's very similar to what we had with the smooth or continuous manifolds. I mean, we defined, now let me remind you how we define smooth manifolds. So smooth manifold is a ring space M with the sheaf, say C infinity of M. C infinity of M is a subsheaf in functions on M, such that locally, that means that at each point has a neighborhood which has this property. M C infinity of M is isomorphic to an open ball B inside R n with a Cm of B sheaf of smooth functions. Okay. I will emulate this definition and give you a definition of algebraic variety in similar terms. Of course, you can't do it with usual topology because there's no such thing as if you have some open set like a ball, it's not reasonable to define algebraic functions on it. A ball is not algebraic. And of course, you can fix algebraic coordinates on a ball, but it's not natural and it won't work. So for varieties, if you need to work, you have to work with Zariski topology. Fortunately, we know what it is, because we had it several times. Now let me tell you something about Zariski topology. This is an important thing. It is that Zariski topology, every set in Zariski topology is compact. Not only like even open sets. This is because there's a theorem that if you have an open set which is compact, it's closed. Sorry, if you have a set which is compact, it's closed. This theorem depends on Hausdorff. If you forget about Hausdorff, no longer true. Okay, so first, let me explain to you about the base, the definition. Suppose I have M topological space. Base of topology is a here I didn't assume that it is closed under taken intersections. Let me assume that. I think sometimes it's assumed, and it will simplify the next statement. Base of topology is a collection of open sets U alpha such that each open set is union of U alpha and intersection of finally many elements of U alpha belongs to U alpha. This is important for the following reason. Remark: if you have a sheaf is uniquely determined, F is uniquely determined by F of U alpha and restriction map from F of U alpha 1 to F of U alpha 2, where you take all U alpha 1. Of course, U alpha 1 should contain U alpha 2, U alpha 2 inside the base. This is why we are interested in the base. And proof is almost trivial. Proof. We just use gluing F of U. So we have a sheaf. We want to recover a sheaf from its restriction to open sets which belong to a base. F of U, you take so U is a union. U is a union of O alpha. Recover F of U, where U is a union of O alpha. Okay, we have F of U is by definition of a sheaf. It's a collection. The set of all collections Fi inside F alpha inside F of U alpha. We know restrictions to open sets, and we know the the restriction maps from open sets to small open sets from the base. F alpha restricted to U beta is equal to U beta, F beta restricted to U alpha. Where alpha and beta belongs to this, let's call this index set I. Okay, so you want to recover F from restrictions to the base. Good. Your base is covered, is a union of U alpha, where U alpha are in the base of the topology. F is not in the base topology, but U alpha is in base topology. You know what is F alpha restricted to U alpha, and you know how to restrict to a smaller, to intersections. So these are two guys belonging to F of U alpha intersected with U beta. So intersection belongs to the base. So this belongs to the base. And this, you know what all U alpha and all U beta, you have these sets and you have the restriction maps. So this gives you, this is a good, this is precisely f of U if you had a sheaf F by the axiom of sheaf. Okay, so this is why I need a base. So for Zariski topology, there is a very nice base. So claim let M be affine variety, and you H, the set of all open sets of form M without ZA or DH, where H is a function, regular function, and DH is zero divisor. That is all the set of all points where this thing is zero. It's a principal divisor by definition. Of course, not Zariski open sets are like that, because, for instance, you have C square without zero. It's not C square without divisor. In fact, it's not hard to see that, and I think we have discussed that any rational function which is defined on this set, in fact, is defined on all C square. So this is definitely not of this form, because for this open sets you can always find algebraic function, I mean rational function, which has pole on this DH. Okay, then UH is a base. Okay, for intersection it's clear. This is why I forgot about it. If you have an intersection of two such open sets, you can just multiply your functions. So intersection of sets means that you take union of the divisors. And of course, if you have zero divisor of H, zero divisor of H prime, their product has zero divisor, which is union of their zero divisors. Okay, now let's prove it. Okay, what is an open set? In Zariski topology, U and M is Zariski open if M is, U is Z without, M without Z, where Z is Zariski closed. that is a subvariety. Okay, then you represent Z as an intersection of divisors. DH, where H are generators of ideal defining Z, right? Z is common zeros of certain collection of functions. And each of these functions has a divisor at zeros, and Z is just intersection of all these divisors because it's common zeros of collection. Good? Then U is union, complement, after take complement, union, and intersection are exchanged, UHI. Good. So this is, now compactness. So is it proposition? It's again trivial. So the idea of Grothendieck, who developed all this mathematics, was that after you made correct definitions, which can be complicated, all theorems becomes trivial, and this is what happens. You see that the definitions are complicated. Things like Zariski topology or sheaves, but all the theorems become trivial. So let's prove it. Suppose you have X is union of U alpha. U alpha is Zariski open. Then it's a cover. Then there exists finite subcover. X is equal to U1, well, U1 union with U2 and so on. What happens? Okay. And so on, UN. So proof. Okay, we have, let's just take one, another, and so on. Then you take union. Union of finitely many open subsets is always open. Oh, even infinitely many. So you take, you can increase that and increase until it stops. If it stops, you have finitely many subsets, or if it doesn't stop, you would have infinitely increasing subset. So if false, there exists infinite chain. Zariski open subsets. U1 inside U2, inside U3, inside and so on are not equal. Okay, the complements. Sorry. Complements give decreasing sequence. So you have Z1 containing not equal to Z2 and so on, where Zi is M without UI. Okay, this cannot happen because this would give you an increasing chain of ideals, which can be. Am I clear? Questions, comments? Another thing which we need is that regularity is local in Zariski topology. So we want to recover, to prove that regular functions are a sheaf. And to do that, in Zariski topology. To do that, we need to have the gluing axiom. So let's state and prove the gluing axioms for regular functions in Zariski topology. Okay, so you have, is it theorem 1, right? Theorem 1. Of course, we don't know about, we still haven't defined what is regular function on open subset which is not affine. But we know about affine. So these guys, the complement to divisors, are affine, right? Everybody remembers that? Please raise a hand if you remember that it is affine. Thank you. Okay. So suppose you have M is a union of U alpha, where U alpha is M without principal divisor. Like that. And suppose you have F alpha inside O of U alpha, regular functions. That makes sense because these guys are affine, such that F alpha restricted to the intersection, U alpha intersected with U beta, is equal to F beta restricted to the same, U alpha intersected with U beta. Then there exists F inside of M, such that F restricted to U alpha is F alpha. This theorem is slightly differently, I stated slightly differently, but you can easily see that it is the same. In fact, I proved this theorem. So proof, step 1. Since M is compact, we can assume that F alpha, the set, is, or U alpha, is finite. Yeah, and let me first state that, so this is step 0. Step 0. O of U alpha is localization. O of M, H alpha minus 1, where H alpha is the corresponding, the function with zeros in M without U alpha. I mean, this is, U alpha is a complement to the principal divisor, so such a function exists. Then F, okay, this is localization, but then intersection, well, you can take, okay, let me, I want to to tell you that you have map from OM to O of U alpha. Of course, it is an embedding for, here I stated it as about a rational function because well, what is stated here is I consider a function with values in C. I didn't say that it is regular. I just say that it is a function. But it is a function which obtained from a restriction on each U alpha. But on intersection of this U alpha, the function f alpha do agree. So you can glue that and you obtain a certain function. What I'm going to tell you now is that this function is first rational, and second, it has no denominators. It's in fact regular. So in step 0, I was going to tell you that you can check that such a function is automatically regular, but this function is defined. So we don't need to worry about this because it's a function, right? Okay. So let me erase this step 0 and continue with what I'm going to tell you. So we can assume this is finite. Okay, and then intersection of all Z alpha. Let Z alpha is M without U alpha, and H alpha corresponding function defined as here. Since intersection of all Z alpha is 0, this is because union of all U alpha is M. H alpha, the ideal generated by U alpha, H alpha, contains 1. I mean, it's not an ideal. H, well, contains so the submodel generated by H alpha contains 1 submodel in OM. If it doesn't contain 1, it's a proper ideal, but then it has common zeros. And if it has common zeros, this means that this intersection is non-empty. Right? Am I clear? Completely? Good. Contains 1. You have some it should be here M on the top. 1 is equal to sum of G alpha, H alpha. H alpha, where G alpha is regular functions, belong to OM. Step 2. Okay, so OM of H alpha minus 1 is by definition O U alpha. It's a definition. Then you have a regular function, f times H alpha power n is regular for each alpha for some we choose n sufficiently big. I mean, it depends on alpha, but there are finitely many, so you can always choose the biggest one. And then take the sum. 1 is equal to sum of G alpha H alpha. And suppose so when I use this sum, it's from I equal 1 to m. So there are m terms. You take the power times nm, big N, small m. And then I multiply it by f. I obtain f is equal to that. But this is 1. On the other hand, this is regular for the following reason. So you take, there are lots of monomials. But in each monomial, one of these terms has power at least n. Because, I mean, it's power nm. There are m different monomials here. But you take nth power times m. So the smallest power which can happen is you have all different monomials in power of n. Otherwise, you would have at least one of these monomials big enough. So this product, term by term, is a regular function. And this is regular. Good. So we proved a certain thing. We proved that. Questions, comments? Regular functions are a sheaf. Let's define first step. So as I told you, to define a sheaf, it's sufficient to define it only on the open subsets in a base. So you have M, affine variety. You have U alpha, all complements to principal divisors, which is a base of Zariski topology. And you have O U alpha is regular functions. Of course, you have restrictions. If you take an open set, you restrict it to a smaller open set. The regular functions are obtained like that. You just take the 0, and the second open set is obtained from the first by taking zeros of certain function, just localized by this function. And then restrictions, you take O alpha, or U alpha, in O U alpha intersected with U beta. U beta is M without Z beta. H beta is a function with zeros on Z beta. Then this is localization. Map. You take O U alpha and you map it to O of U alpha localized in H beta. This is clearly this is just identity map. You just restrict a function to an open subset. So this works well with respect to the to the sheaf axioms. We can extend this to a sheaf by gluing. So for each open subset, Zariski open, of course, U inside N U is a union of U alpha. U alpha are complements to divisors, complements to affine. Use Schiff axioms. Gluing, essentially. Gluing to define O of U. And now I claim that it is a sheaf. So what is actually this thing? So the regular functions, or U, are rational functions with poles on the complement. So remark, regular functions on U inside M are the rational functions with poles on complement. M without U. So by definition. So for each small open set, the corresponding regular functions are just rational functions with poles on its complement. So if you take, so this gluing is essentially taking intersection. So if you have open set U, you are interested in functions which are restrict to each U alpha by given regular functions. These precisely functions which have poles outside of U alpha. So theorem, this is a sheaf. Proof, you use theorem 1. Yeah, theorem 1. So you need to check gluing, but we just did it. Of course, we did it only for affine sets, but there's nothing to prove for the rest, because we just, for the rest of the sets, which are not affine, we just defined sheaves by gluing. So there's nothing to prove. But for gluing, of course, we have to prove it. Okay. This is the last slide. Okay, yeah. Now definition of algebraic variety. So definition, algebraic variety is, it's a definition which is almost word by word the same as the definition of smooth manifold which I gave. Is a sheaf, space with sheaf of functions which is locally isomorphic to affine variety with the sheaf of regular functions. So you cover your space. The next slide we will example, but let's first have a break. You cover your space by open sets. Each open set is a affine variety. Then the gluing is given by rational functions, like. So what you have is essentially you have some, for each two sets, you have a smaller, the intersection is a smaller, well, it can be a union, but it can be a union of affine open sets, but it is covered by affine open sets. And these affine open sets are, again, affine varieties, which are birationally isomorphic to the first one, because your restriction is just taking away some divisors. And then you glue things together. In particular, the general point, I mean, the section, if this was irreducible, then the you have a well-defined space of field of rational functions for each algebraic variety. But then what happens is that you have many affine varieties somehow glued, which are obtained by this field as sub rings in this field. Okay, let's have a break, a short break. Now it's 29 according to my clock, so let's meet back in 34. You can ask questions or just enjoy your time. Like varieties. Let me define now the morphisms. Morphism of algebraic varieties is a map M1 to M2 such that pullback of regular functions is regular. And of course, continuous in Zariski topology. Continuous in Zariski topology. Otherwise, I mean, if you want to speak of pullbacks, you really need to have pullback of affine is affine, or at least is union of affine. So otherwise, it won't make sense. Okay. So what does it mean, pullback of regular is regular? Of course, if you have a Zariski, if you have an, so it's now you restrict to, of course, if you speak of pullback as regular, you need to speak of things which are affine. So you have a map of affine varieties, M1 to M2, affine now. And this, since it's affine, it's subset in Cn. So you have coordinate functions, x1 dot xn coordinate functions. You have f, and our assumption means that f star of xi is regular. Okay, now f star of xi is by definition applied to z. So you have z inside M1. Applied to z is equal to xi of f of z. So this is coordinate component of f, right? Number. So it is regular precisely when the map is defined is polynomial, because this means that it is polynomial in coordinates given by xi. Am I clear? So this definition coincides with the definition which we have for affine varieties. Clear? So we just extended the category, but we didn't change the morphisms. Morphisms, there are more objects, but the morphisms are the same in affine, category of affine varieties and categories of algebraic varieties. Now let me give you some examples. Of course, the first example is affine varieties. It's not an interesting example, but it's trivial. So the better example is projective. This is why I was forced to give you this set of complicated definitions, because this really simplifies. Of course, you can do Italian style. You can avoid give everything without using sheaves. But at some point, it becomes unbearably complicated and really stupid. So it's necessary to do high tech at this stage. Okay, now example. you have n inside C Pn projective variety. Okay, it's a variety which is given by a set of homogeneous it's zero set of homogeneous of a collection of homogeneous function or great ideal. And let's define the corresponding algebraic variety in the previous sense. You have affine charts. A k is so you have homogeneous coordinates x1, x0, xn, and then you have x. So homogeneous coordinates x1, x0, x1, xn, but they're defined up to multiplication by a constant. Now you have affine coordinates. We assume that we take affine cover, which is CP, which is the set of points such that xk is non-zero. And then AK coordinates has coordinates A0, x0 divided by xk, x1 divided by xk, and so on. They're columns, but you don't need them because now it's really affine coordinates. You have one in the middle, but now it's well defined. It's not defined up to a constant, it's well defined coordinates. Okay. These are fine. And now M intersected with AK is defined by the same ideal. You just plug AK equal 1. So you're no longer homogeneous. You have now non-homogeneous ideal, but it's still an ideal. And clearly it vanishes precisely in points which intersect. So this is algebraic. M intersected with AK is algebraic. There's nothing to check. Okay, what is needed to check is that the transition functions are morphisms. You have to check that transition functions are. Now I'm slightly overreaching because I give you this definition, but then there is, like for the usual smooth manifolds, you can do with charts and atlases, as usual. If you have a definition in terms of sheaves, you take. You can have a definition in terms of atlases as follows. You have M is a union of UI. UI are affine. And I intersected with UJ. Well, it's not necessarily affine, but let's assume for now it's affine as well. And then you have, this gives you two algebraic structures. It belongs to UI, it belongs to UJ. If you want, now what we have to have is that every point has a union which is affine, and then the sheaves agree. For that, you need, of course, the map. You have a map from UI intersected with UJ. This is openly embedded to UI, and this is openly embedded to UJ. So it has two algebraic structures. And for the sheaf to be correctly defined, they have to agree. This gives a transition function. Like for smooth varieties, for smooth manifold, sorry, if you have a smooth manifold, you have to agree that your charts on intersections give you smooth transition functions. Here we have to check that algebraic functions, the transition functions are algebraic, are polynomial. This is the only thing we need to check to prove that something is an affine variety. Just use chart analysis, gluing, and so on. Okay, so we're interested in transition functions. We have a coordinate chart here. We have coordinate chart M intersected with AK, AL, and we know what is the gluing map. So the gluing map from AK to AL takes a point, it is a multiplication by xk divided by xl. Is a multiplication by xk divided by xl. Right? Now this is a regular function on our complement. Because our complement is something where, I mean, this is a well-defined function on the complement, and in fact it is invertible. So your transition functions are algebraic in these coordinates. Good. Okay, another example is, of course, the complement to a variety. So example, you have a Z inside M, then a Zariski closed, then M without Z is algebraic variety. It's not affine. For instance, if you have C squared without 0, you can easily see that all regular functions, which are global regular functions on C squared without 0, which are regular everywhere outside of Z, they're regular on Z. Because they, if it is a meromorphic function, it has to have a divisor, a pole divisor somewhere. And if it has no poles, this means that it is actually polynomial. Just use the factoriality of the polynomial functions. You see that if you have any rational function, you just take away all common divisors of the denominator of the top and bottom, and you obtain in the denominator a divisor which such that the it is a pole. Okay, so you have algebraic variety because it is M without Z is a union of M without Z alpha, where Z alpha are principal divisors, such that Z is intersection of Z alpha. And it's clear that transition functions are again, I mean, it's transition function from a variety to itself, essentially. Well, you take away one divisor, take another divisor. This means that your transition functions. So if you have M without Z alpha intersected with M without Z beta, So here you have this are both affine. This is both affine, and then this is the corresponding regular function ring is L of M, where you localized by H alpha. Here you have O of M, where you localized by H beta. And here you have the intersection is O of M localized by both H alpha, H beta. So these two guys are embedded here, and this embedding is compatible with algebraic structure. Okay. Before I'm going on, let me ask you something. Do you want me to give you more examples of projective varieties without things like morphisms? Or do you want me to explain you morphisms slowly, like with sheaves? Because without sheaves, it would be not worth it. With sheaves, and then give you examples. What is your preference? Anyone? So who is for the first? For sheaves? And who is for more examples before sheaves? 2 against 3 or 4? So who is for sheaves? For examples again? 3, 4. Oh, good. So next time I will give you minimum definitions and examples. It's unfortunately it's hard without any definitions at all. But at least we can do something. Okay. And now let's do with. I will go on slightly in the direction of more fundamental stuff. But next time I would stop this fundamental direction and do more examples and then back. So you have things like sheaf of models. This is an important notion. The obvious idea is that if you have a map of homomorphism, ring homomorphism, A to B, then B is a model. Right? You can take elements of B and multiply them by an image of, if you have phi, so B, A times B goes to phi of A times B. This is, and also a B model becomes a model by the same law. Okay, definition. Suppose you have sheaf of rings. F, sheaf of rings. And B, a sheaf. And suppose that a B of U, the space of sections, for each U, B of U is equipped with F, with a structure of F of U model. And of course, this should be compatible with restriction maps in the following sense, that for each U inside V, you have F of V restricted to U homomorphism to F of U. You have B of U. This is restricted to B B of V, sorry, B of V restricted to B of U. Now, you can consider, so f of u is f of v model. And this is model over model over. So this model over that, this is model over. So B of V can be considered as, sorry, B of this is model over that, then this is model over that. And this model over that. This should be a map, morphism, of f of V models. In other words, if you multiply, you can multiply something by a function of here, or you can restrict and multiply by restriction. This should be the same. This is precisely what is said by this being a map of models. Okay, this was definition of sheaf of models over a sheaf of rings. For example, what you can think of is, let's take the tangent, the vector fields. The vector fields on a smooth manifold. You multiply vector fields by functions. This means that they are model over functions. But on the other hand, they are sheaves, because you can restrict vector fields to a smaller subset. It will be vector fields on a smaller subset, but then this restriction is compatible with the multiplication by functions. Okay, free sheaf definition. Free sheaf, sheaf of f of u models is f of u power n. Just n copy, direct sum of n copy. This is like free model, but with sheaves. And now, locally free sheaf. I told you about isomorphisms of morphism of sheaves, right? Now, morphisms of models, sheaf of models are just morphisms of sheaves, which are compatible with multiplication by functions. There's nothing complicated on that. So locally free sheaf is sheaf which is locally isomorphic of models, locally isomorphic to a direct sum of f of u. Globally, they are not isomorphic, there are examples. The typical example can be seen if you consider a Möbius strip. So you have a Möbius strip. Let's think of it as a space of lines on, so it rotates, like you have direction here, you have direction here, you have direction, now you have direction here, here, now you have here, it should be opposite direction, good, all right, now you have here, here, and here. So you go around, and the direction of the strip rotates. But the strip is R's. It's copies of R over a circle. Then the space of sections. You can multiply a section by a function. But it is non-trivial because you have no sections of this Möbius strip map which are non-zero. I mean, it rotates. It's positive in that direction, but if you go around, it becomes negative. This is an example of a sheaf, which is the space of sections of the Möbius strip, which is locally trivial, locally it's just a product, but globally it's no longer a product. It rotates. Okay. Now there is an important notion of coherent sheaves. I am pretty much out of time, so I'm not going to give you much. But this is really something you really need to work properly with projective varieties. So you define coherent sheaves, locally finely generated, finely generated sheaves of finely generated models over regular functions. It's coherent sheaf. Line bundle is locally free sheaf of rank 1. Rank is this number. And this is actually a line bundle over the ring of functions, because locally it's just a product with R. So it's maps to R, which is the same as functions. So a line bundle is, example is a trivial bundle. Okay, I'm out of time. So next time we shall see more examples, like Veronese maps, a Gray variety, and more examples until we are sick of it, and then we shall go with the coherent sheaves again.